Okay, today I will go over chapter 1 review in from our textbook. Now, I have seen the questions and there are some of them I know pretty sure I will not ask in the test, so I may go over of them briefly only. In fact, I will put a mark that I will not ask those kind of questions. But I will try to go over them briefly anyway. Okay, let me start. Again, this is from the chapter 1 review in our textbook. Number 1, let f be a function whose graph is given. Estimate the function of f2. f2, let me use slightly different color. So 2, if 2 is here, then the y is approximately 2 point something, but it's not 3, right? It's not 3. So approximately number 1, a f2 is approximately 2.7. Okay, maybe 2.6, maybe 2.7, but from the graph I think it's more into 2.7. But if you say 2.6, it's okay. Now part B, estimate the values of x such that fx equals to 3. Which means if the y equals to 3, what is the x? It's approximately 2.3. Is it right? So if x equals to 3, x is approximately 2.3. Actually, there's one more. There's one more somewhere around here. Somewhere around there. So 1, 2, 3, 4, 5. Approximately 5.5. Right? Now that's because the graph is given, so we use the graph to do the estimation. Part C, state the domain of this function f. The one provided to us, only this part here, so I will use this graph only as a reference, -1, -2, 3, 4, 5, 6. So the domain will be approximately, from the graph, is from -6 to +6, while the range is the y component from -4 to +4. From -4 to +4. On what interval is the function increasing? Increasing means the place or the axis where the slope of the graph is positive, right? We can see that it is actually increasing from here up to here. Like imagine if you walk through this from the left to the right, you know that you will be going up from -4, increasing on from -4 to +4. And then part F, is the function even, odd, or neither even nor odd? Explains. A function is odd if it is symmetric with respect to origin. Okay, as we can see here, for any points you pick on the right hand side, let's say I pick this one point here, and I reflect this with respect to the origin, I have the other point also on the graph. And the thing is, it applies to every one of the coordinates. If I reflect this with respect to origin, I will get this one here. So since the graph of that function, so it has to be a function first of all, okay, of the function is symmetric to origin then fx, the function, is odd. Okay, that's for question number 1. I don't think I will ask this kind of question in my test, but the underlying idea is of course necessary. Okay, now number 2, determine whether each curve of the graph of a function of x, if it is, state the domain and range. Actually, we can even if it is not a function, we can still state the domain and range. Okay, now the first graph here, this is not a function. Why? Because it doesn't satisfy vertical line test. While the second graph here, every vertical line will intersect the graph at most once, so it is a function. Okay, now how about the domain and range? For first graph, let's call that 2a. The domain is from -3 to +3, and the range is from -2 to +2. While for the second graph, which is a function, okay, the domain is from -3 to +3 also. While the range is from the minimum value of y is -2, the maximum value of y is 3. Okay? Yeah, so let me emphasize again that even though the graph is not the graph of a function, but since it is a graph, then we should be able to see what's the domain and the range. Okay? Again, number 2 is not the type of question I usually ask in my test, but the underlying idea is necessary. Number 3 is the type of question. In fact, I can almost guarantee you will see that type of question in my test. Okay, so evaluate the difference quotient for that function. So we have fx for number 3, fx equals to x squared minus 2x plus 3. Okay, so what is f of a plus h? F of a plus h, we replace the x by a plus h. Then we get a squared plus 2ah plus h squared minus 2a minus 2h plus 3. Let me simplify this further. Just open the parentheses. I don't think I can combine any like terms because there is no any like terms here for now. Okay, while fa is simply replacing x by a. So the difference quotient is given by f, let me write down the formula first, fa plus h minus fa over h. So this is basically the difference quotient of the function at a. Okay, this is the difference quotient of the function at a. This is equal to, the top left is a squared plus 2ah plus h squared minus 2a minus 2h plus 3. That's for the top left, minus the top right, a squared minus 2a plus 3 over h. And then from here we see we can do canceling. This will also cancel this will cancel this. So we get on the numerator 2ah plus h squared minus 2h over h. I can factor the h out, and later on that will cancel with the h at the bottom. Okay, so the difference quotient is 2a plus h minus 2. Okay, in your test, for sure, you will have at least one difference quotient problem. At least one. Number 4, sketch a rough graph of the yield of a crop as a function of the amount fertilizer used. Honestly, I don't really have too much idea of this. Let's give it a try. I will give it a try. Okay, so let's say this is the amount of fertilizer. And then this is the yield. Now suppose the amount of fertilizer is 0. Do we expect to have some yield? I think so, but it's not too much maybe, huh? Okay, but as we increase the amount of fertilizer, then I think the yield will increase, right? Okay, but I think once we have too much fertilizer, then the yield will become not efficient anymore. In fact, if you have all fertilizer, I think no crops will be yield, right? Okay, but this is just approximate. Okay, what I did here is just this is just based on the assumption that even if we don't use any fertilizer, there's a chance that we'll still gain some yield. Okay, but we put fertilizer to increase the yield. But if we put too much fertilizer, then it will negatively affect the yield. Okay, and if it's way too much, then it will kill the crop instead, you know. Okay, now this is not the type of question I usually ask in my tests. Now, I don't have interest in that kind of question, especially it's way too vague, you know. Okay, number 5 to number 8 are the type of question I would like to ask. Find the domain and range of the function. Write your answer in interval notation. Okay, so number 5, we have fx equals to 2 over 3x minus 1. The domain, that is all real numbers except 1/3, right? But they want us to write it in interval notation. So I will write it as, if you imagine, it's all real numbers except 1/3, right? So the interval notation will be negative infinity up to 1/3, not including 1/3, union 1/3 to infinity. How about the range? How about the range? Now, as we can see from that function, actually, the proper way to find a range is to rewrite that into the inverse. That's actually the proper way to do it, you know. But if you happen to be able to see, remember the graph from pre-calculus, okay, now notice that 2 over 3x minus 1 cannot be 0, right? Why? Because the numerator cannot be 0. Okay. Another reason is that's actually the horizontal asymptote, and this function is 1-to-1. So there's actually a lot of things to say here. Let me just do it appropriately, the proper way to do it. The proper way to do it is by realizing that this function is 1 over x, coming from 1 over x, okay? And then we rewrite that as 1 over what is that? X minus 1/3. And then from there, we multiply by 2/3. Okay, now the range of 1 over x is all real numbers except 0. When we move that to the right 1/3, then the range will be, oh, I'm sorry, stay the same, not the domain, it's the range. So the range stays the same because we just move it to the right by 1/3, right? And then when we stretch that by a factor of 2/3, the range will stay the same. All real numbers except 0. So from here we say, oh, the range is -infinity up to 0, union 0 to infinity. That's for number 5. How about number 6? We have a function gx equals to square root of 16 minus x to the 4th. What is the domain? Well, the domain is all the real numbers where the radicand, the guy inside the radical, has to be at least 0. So we need to solve 16 minus x to the 4th to be at least 0. It means x to the 4th okay, so it means x to the 4th is at least 16. Now, to solve a polynomial inequality, actually, I don't need to go this far. To solve a polynomial inequality, we're supposed to do the 3-step procedure. I mentioned this in class before. Okay, the first one, we need to find the critical numbers. At what numbers this is exactly equals to 0. Okay, so we get this is 4 plus x squared times 4 minus x squared equals to 0. Now, of course, 4 plus x squared is always positive. Always positive, not even 0. Okay, so we will just consider the 4 minus x squared. I factor it further. So we get the critical number x equals to -2 and x equals to +2. And then we do the sign graph. At -2 and 2, the polynomial 16 minus x to the 4th will be 0, right? And then when x equals to 0, that will be positive. When x is greater than 2, that will be negative. X is less than -2, that will be negative. You can just try picking a testing point. Let's say if you pick x equals to 5, when x equals to 5, 16 minus 5 to the 4th, is it positive or negative? That's 16 minus 625, that's negative, right? Okay, then from there we go on further. Reading, we need 16 minus x to the 4th to be non-negative, right? So the domain is the interval where we get 0 or positive. Okay, as for the range, notice that 16 minus x to the 4th is maximum, has maximum 16. Okay, so the square root of 16 minus x to the fourth has maximum the square root of 16, which is 4. But on the other hand, the nature of square root itself has a minimum. Square root of anything is at least 0, right? And 16 minus x squared may be 0. So the range here will be from 0 to 4. Okay? Now, number 7, number 8 happens to be on the easier side. So this is my type of question. This number 5, especially number 5, number 6. Especially number 5, number 6. Number 7 and 8, you will see it's way too easy, such that I don't think I will ever ask them. The domain of trigonometric functions, sine x, is all real numbers. Okay, when you add with a constant, the domain will still be the same. The domain is all real numbers. Okay, now how about the range? The range for sine x we know is between -1 to 1. So 1 plus sine x has the range, if you add 1 both sides, has the range from 0 to 2. Okay, for number 8, the domain for cosine is all real numbers also. When you add a constant, it will still be all real numbers domain. The range, however, for cosine anything, the range is between -1 to 1. So 3 plus cosine 2x has a range from 2 to 4. Okay. Number 9, suppose the graph of the function is given. So suppose we are given that. Describe how the graph of the following function can be obtained. Now, this is not my type of question that I put in the test, but let's review a bit on how we will obtain the new graph from a given graph. For 9a, y equals to fx plus 5. What this graph has to do with the original graph of fx. This is fx. I think I should say the graph of fx. The graph of fx move up 5 units, right? Because we add 5. The function, we add 5, so we move up 5 units. Part B, how about y equals to f of x plus 5? If you replace the x by x minus c, then it will move to the right c units. If we replace x by x plus 5, this will be move left 5 units. Okay, we move to the left instead. Imagine this one. Suppose if you have x squared and then you replace the x by x plus 5, what will that be? Okay, now that's for part B. Part C. Y equals to 1 plus 2 times fx. Now, first, according to the order operations, we multiply by the function by 2 first. Okay, and multiplying the function by 2 means we stretch by factor of 2. Okay, and then the plus 1 will be move up 1 unit, then move up 1 unit. Okay, part D, how about y equals to f of x minus 2? That's a move 2 units to the right. Okay, and then minus 2, that's 2 units down. So this is 2 units to the right. Move right 2 units. And then down 2 units. Okay. Now, how about part E? 9e, y equals to negative fx. If we multiply the whole function by negative 1, that's reflect with respect to x-axis. Okay, negative fx. We reflect with respect to x-axis. Okay, and then part F, what is y equals to 3 minus fx? Now, we can see this as 3 plus negative fx, right? Or maybe we write that as negative fx plus 3, right? Okay, is it better? Now, then we can see, oh, this is first we reflect with respect to x-axis. The graph will reflect the graph with respect to x-axis. That's what we do first. And then we move up 3 units. Okay. Now I see question number 10 is quite similar, so I will not go over that anymore. But basically they give you the actual graph and then you play around with that, you know. But I will skip that one. The underlying idea is required though. Okay, the underlying idea. In fact, you will see that number 10 to number 11, I mean 11 to 16 is the type of question I would like you to be able to apply those concepts from number 9 and number 10. Okay, let's start with number 11. Number 11, the basic graph is x cubed, and then we move 2 units up. So suppose I have this coordinate system. Okay, so the graph of x cubed has vertex at origin 1, 1, 2, 8, 2, 6, like this. It looks like this. And we know this is an odd function, right? So that's this is what it looks like for x cubed, right? Now, then if we add 2, it means we need to move the graph 2 units up. Or we can also move the x-intercept down by 2 units, and it will give us exactly the same graph. Okay, that's for number 11. So we take the graph of x cubed and then move it 2 units up. Number 12, f of x equals to x minus 3 squared. This is the graph of x squared. Move to the right 3 units. So the vertex becomes 3, 0, approximately like this. Now, when I ask you to graph this, the resulting graph here, I do expect you to give me, you bubble it, please, bubble the special coordinates. Okay, as if you are saying, hey, you know what, the graph passing through these coordinates. Number 13, square root of y equals to square root of x plus 2. The basic graph is square root of x, but we move 2 units to the left. Okay, the vertex now is negative 2 comma 0, and then 1 unit up, 1 unit to the right, 2 units up, 4 units to the right, 3 units up, 9 units to the right. So the graph is approximately like this. Notice that I bubble my important coordinates. Okay, the graph number 14, that's y equals to 1 over x minus 1. The basic function is 1 over x, right? Let me enlarge this a little bit so that we have a better visibility. Now, the original graph is like this. This is what 1 over x look like. This is what 1 over x look like. Do we have to memorize this, Thomas? Yes, you need to. In fact, you're supposed to have memorized this when you took pre-calculus. Okay, that's the graph of 1 over x. Now, what happened if we replace the x by 1? It means we move the graph 1 unit to the right, or we can also think another way. We move the coordinate system 1 unit to the left. So that's what it will look like. Okay, that's for number 14. Number 15, 1 plus cosine 2x. Number 15, what is the function again? The name of function, gx. So gx is 1 plus cosine 2x. Now cosine 2x means we stretch that by factor of 2. So originally the graph is, let me get the coordinate. So let's say the graph is, this is 1 unit here. Let's say this is 1 unit, this is negative 1, and this is pi over 2, this is pi, and then this is 3 pi over 2, and this is 2 pi. Now, but the period originally, the period of cosine originally 2 pi, but because we shrink that by a factor of 2, then the period becomes just pi. Okay, the period equals to 2 pi divided by the coefficient 2. Okay, it means it makes one full cycle in pi. One third is approximately 60 degrees, so approximately here. So the graph looks like this. Hold on. No, that's not what the graph looks like. At pi over 4, it already dies down. So the graph will look like this. That's what the graph look like. Now, and then, because this graph is repeating, so I will copy paste this. I will copy paste that. Hold on. Here. even though I need to delete a couple things though, not to confuse. So this is 5 pi over 4. This is 3 pi over 2. That's 2 pi. And I also copy paste that to the left. Okay, this is pi, negative pi. Like that. Okay, and on, of course, and on. So let me put an arrow here that it goes infinitely far. Okay, that's for number 15. Number 16 is a piecewise defined function. I don't have space. It's a piecewise defined function. Let me copy the function here. Number 16, fx is 1 plus x if x is negative, 1 plus x squared if x is non-negative. Okay, so let's do the positive part first. 0 plus x squared. 0 plus x squared looks like this. For x equals to 0 or positive, right? While to the left of that, we have 1 plus x, means the y-intercept is 1 and the slope is also 1. So the graph to the left of that looks like this. Then let me do the bubbling just to make sure that the reader knows that the graph actually passing through these coordinates. Okay, that's for number 16. Let me go on to the next question. Determine whether this function is even, odd, or neither odd nor even. This is my type of question. So expect me to ask this type of question. How do we show that a function is even or odd? Okay, a function is even means we need to show that f negative x equals to fx. If we reflect with respect to y-axis, we get the original function back, the original graph back. A function is odd is when we reflect with respect to a y-axis, we get the opposite of the y. Okay, so part A, how do we show that this function fx equals to 2x to the fifth minus 3x squared plus 2? Take a look at f negative x. Replace x by negative x. Simplify that. And show that if it is equals to fx or equals to negative fx. Okay, now this is clearly not equal to fx, right? Okay, and if we factor the negative out, we get 2x to the fifth plus 3x squared minus 2. That is not equals to negative fx either. So f is neither even nor odd. Okay, part B is fx equals to x cubed minus x to the 7 even or odd. Yes, I circle it, so yes. The one I circle means yes, the one I cross out means no. Do you notice that? Yeah, I circle it. Means yes, this is the type of question I usually ask in my, even in my pre-calculus class. So take a look at f negative x, replace x by negative x, and simplify. Now, of course, we can see here this is not equals to fx. Okay, so from there we see that this is not even. Okay, but if I factor the negative out, I get this is equals to negative fx. Okay, so fx is odd. Part C. How about fx equals to 1 minus cosine 2x? Now we know cosine is an even function. Okay, so f negative x equals to 1 minus cosine 2 times negative x. That's 1 minus cosine negative 2x. Yes, that's what I explained here. Yeah, a function is even for what, odd for what. Okay, so let me box it. But then cosine negative equals to cosine positive. We learned that in pre-calculus, right? And from there we see this is equals to fx. So from here we say that this is f is even. Okay, we're supposed to also check that if a function is if the same function is odd though. So if I factor the negative out, notice that if I factor the negative out, I get negative 1 plus cosine 2x. This is not equals to negative fx. So this is not even, not odd. But you will see there's only a very, very rare case, only one function. There's only one function that I can think of that is even and odd at the same time. So once we know a function is even, then it won't be odd anymore. Okay, the function that is even and odd at the same time is fx equals to 0. Okay, as far as I know, this is the only function that is even and odd at the same time, both even and odd. Okay, but think about the proof though. Can you prove this? Okay, a challenge for my for my calculus students. In fact, I did ask that kind of question in my pre-calculus. Okay, show that fx equals 0 is the only function that is both even and odd. Or sometimes I say that rephrase that, find a function that is even and odd at the same time. Okay, part D, fx equals to 1 plus sine x. So if we take a look at f negative x, this is 1 plus sine negative x. But sine negative is negative sine. It's an odd function, right? Okay, so you see that this is not equals the original function. Even if we try to factor the negative out, we don't get, this is not equals to negative of fx. So fx equals to 1 plus sine x is neither. The last one, x plus 1 squared. So part E, fx equals to x plus 1 squared. Okay. So f negative x is negative x plus 1 squared. This is clearly not equals to fx, so it is not even. Okay. If I factor the negative, there's no way for me to factor the negative though. Yes. Let's see, this becomes x squared plus, actually minus 2x plus 1, right? If I factor the negative out, I cannot factor the guy inside anymore, so this is not negative fx either. So this is, so f is neither. Okay, you may imagine the graph, actually, you can imagine the graph, but algebraic proof is the one you need to show, okay? But if you take a look at the graph, you know for sure that it is not an even function nor an odd function because it doesn't have such symmetry. It does have axis symmetry at x equals to negative 1, right? But for even function, we must have axis of symmetry at x equals to 0. And odd function, it must have origin symmetry. Okay, so for part E, we do have symmetry, but the symmetry is not for even nor for odd functions. Okay, now that's for number 17. Yes, this is the type of question I very likely ask you in your test. Number 18. Find an expression for the function whose graph consists of line segment from negative 2 to negative 2 comma 2, negative 1 comma 0. Let me sketch that first. So negative 2 comma 2, negative 1 comma 0, together with the top half of the circle with centered origin radius 1. Oh, so this is basically a piecewise defined function. Huh. Okay, so let's call this the first part of the graph. This is the second part of the graph. Okay, now I will first work on the first part of the graph. Okay, the first part of the graph, line segment containing negative 2 comma 2 and negative 1 comma 0. Let's see, I see a message coming in. No, that is a coordinate. This is not an interval notation. This is a coordinate from the point negative 2 comma 2. Okay, so that's not an interval notation. That's a coordinate. That is a coordinate, not interval notation. So the slope will be y2 minus y1 over x2 minus x1. And this will give us negative 2 over 1. So the slope is negative 2. So the line right now, the line segment is y equals to negative 2x plus b. I need to find what is the y-intercept. Even though I don't need it, but I need to find the equation, right? So let me use negative 1 comma 0 to help. So the y is 0, the x is negative 1. So 0 equals 2 plus b, so the b is negative 2, therefore y equals to negative 2x minus 2. That's for the line segment. Second part, it's a circle with centered origin radius 1. The circle-centered origin radius 1 has equation x squared plus y squared equals to 1. However, we need to get the top half. So y squared equals to 1 minus x squared. Y equals to plus minus square root of 1 minus x squared, since we need the top half only. We take the positive branch. Okay, but we are not done yet though. We are not done yet. We basically done with finding the function for each segment. Okay, now we need to put them together. So the function here is fx equals to negative 2x minus 2 for x between negative 2 to negative 1. Okay, and then the square root of 1 minus x squared for x between negative 1 to 1. Okay, now notice that exactly at negative 1, you need to decide which function it follows. Now, the nice thing is at negative 1, they happen to be the same coordinate anyway, so you can do it this way, that at negative 1, you follow the segment. Okay, but you may say, oh, you know what, I want the negative 1 follows the top half of the graph, and therefore you don't use that at the segment. They happen to be continuous there, so we can use either one. Okay, that's for number 18. That's the type of question I like to ask, so better know that. Number 19. We have fx equals square root of x and gx equals to sine x. Find the function of f composed g. Part A, f composed g of x is f of gx, that's f of sine x, that is square root of sine x. Oh, find their domains. What is the domain here? Well, the domain is when sine x is positive, right? Okay. The domain is when is all the x's where sine x is non-negative. But when will sine x be non-negative? Remember the graph. It is non-negative in the first two quadrants and any 2 pi multiple of that. This one you need to know though from your pre-calculus. Okay, so x has to be, the domain will be in interval notation. Maybe I write it this way. This is all x where x is between 2k pi to 2k pi plus pi for k integer. So if we look at the sketch, I already draw it, so let me just enlarge it then. So it is positive from 0 to pi and then continue again from 2 pi to 3 pi. Okay, from negative 2 pi to pi, from negative 2 pi to negative pi. Okay, so that's the domain. In fact, we can also say the range will be from 0 to 1. Okay, they don't ask that here, so I don't answer that. Part B. How about G compose f of x? That's G of fx. That's G of square root of x That's sine square root of x. Well, sine of anything is well defined, but for square root of x, we can only have non-negative. So the domain will then be from 0 to infinity. Okay, it will not work when x is negative. Part C, how about f compose f? F compose f of x equals to f of x. That is square root of x, right? That's basically the fourth root of x. Maybe I write it this way. Let me slow down. So this is f of square root of x, which is square root of x. Okay. If I simplify this, this is to the power of 1/2 of x to the 1/2. That's x to the power of 1/4, which is the fourth root of x. Okay, but the domain is still the same. It has to be non-negative, right? And the range is again from 0 to infinity. Now, how about g compose g? G compose g of x is g of gx, which is g of sine x. That's sine of sine x. Yeah, but sine x has a all real numbers domain, so this is perfectly okay. We don't need to avoid anything. Negative infinity to infinity, or we can just simply write it as all real numbers. Okay, that's for number 19. Number 20, express the function fx as a composition of three functions. That's also a question I would like to answer. Now, I would like to ask you. Now, when I say I would like to ask you, doesn't mean for sure I will ask that question. No. Okay, I just want to say, hey, you know what? This is a reasonable question to be in my test. Okay, so if I rewrite this capital F function, this is 1 over the square root of x plus square root of x. Let's decompose this into three functions. I can say this is actually 1 over something, right? Let's call this 1 over gx. Yeah, well, so we need to find those three functions. Okay, three functions. It's like basically find the three function fx, gx, hx such that f compose g compose h of x equals to that capital Fx. That's what we are looking for. Now, we don't have to write it in the three different ways. We need to find three different functions that composes to this capital F. Okay, so we need to find three functions such that f compose g compose h give us this function. That's the question. Okay, express this function as composition of three functions, not three different ways, not three different ways, even though we may possibly write it in three different ways or even more. Okay, but all you need to find out is find one way to do it that consists of three functions. Okay, let's do it. That's what I'm about to do. Your question, how is the one I'm about to do? Okay, yeah, so suppose we see this as 1 over gx. Okay, 1 over gx. So my gx now is a square root of x plus square root of x. right? And if I see my gx as square root of something, square root of, call that hx, then my hx is x plus square root of x. Now, the three functions that I get here is not unique. You may find another way. You may find another way. Just make sure that when you compose them, you get this capital Fx. Okay? So it is not unique. So let me start with, let hx be x plus square root of x. My gx be square root of x. Notice that g compose h, x, give me g of hx. That gives me square root of hx, which is x plus square root of x. That's what we have so far. Now, and my fx equals to 1 over x. Notice that f of g compose h of x, the guy that we have up here, is equal to 1 over square root of x plus square root of x. Okay, so those are the functions. So fx equals to 1 over x, gx equals square root of x, hx equals to x plus square root of x, and f compose g compose h of x equals to the big function fx that we had originally. Okay, so the thing we need to do here is to find the function, three functions, such that when we compose them, we get a capital function f. Now, this type of question, even though may not be as crucial right now, but this skill is very crucial later on when we do derivative, because we need to see them as composition of functions. Okay, so basically, can we break these functions, these complicated functions here, in 3 steps? If we need to build this function, how do we build this function? Okay, number 21. This is not the type of question I would like to answer. I would like to ask, but let's answer this anyway. Life expectancy has improved dramatically in recent decades. The table gives life expectancy at birth of males born in the United States. Use a scatter plot to choose an appropriate model, and use your model to predict the lifespan of a male born in year 2030. So basically, what we do is we construct, oh, not this one. We don't need to use this one. We will construct some kind of a scatter plot. Scatter plot, basically you plot these coordinates. So at 1900, let's say is 48.3, 1910, it increases. Okay, after you plot all of them, you will see that, hey, you know what? It seems like the graph get very, very close to, let's say equation of a line, right? It give us a line, and this, let's say this is at 2010. Okay, then you approximate. So maybe I write the plan. The plan to do this problem is, as they say, sketch the scatter plot. Basically, plot these coordinates. okay, for the year and life expectancy. Now, after that, estimate the curve best fit those points. Okay, usually we use a line. Usually we use a line. If we see that the graph seems to get close to a line. Okay, and then once we get that line, then we estimate, find the equation of the line, where x is the year and the y is the life expectancy. Now then, after that, input x equals to 2030, find y. Okay, so from there we can expect to see how long a male born in 2030 expect to live, how long we expect that male to live. That's for number 21. Number 22, a small appliance manufacturer finds that it costs $9,000 to produce 1,000 toaster ovens a week and $2,000 to produce 1,500 toaster ovens a week. Okay, so $9,000 for 1,000 toasters. This is my type, by the way. $12,000 for 1,500 toasters. Now, part A, express a cost, the cost as a function of the number of toasters, assuming that it is linear, and sketch the graph. Oh, okay. So we want the cost as a function of toaster. So the input is toaster. The input is toaster. The output is cost. Okay. So let's rewrite this then as a coordinate 1,500 toaster for 12,000. That's one of the coordinate. 1,000 toasters for $9,000. So I write it as a coordinate first, where this is the number of toaster, and this is the cost, toaster cost. Okay, now because it is linear, then we assume, well, because we assume it is linear, then we need to find two things. First, we need to find the slope. Okay, 12,000 minus 9,000 over 1,500 minus 1,000, that is 3,000 over 500, that's equals to 6. That's the slope. And then as for the y-intercept, y equals to 6x plus, I'm sorry, cost function as cost as a function of toaster. Cost equals to 6 times the number of toaster plus the y-intercept. And you will see that b here in this case in econ or in finance, we call that the fixed cost. So I will use one of the coordinate. Let's say I use $9,000 for 1,000 toasters. That's 9,000 equals to 6,000 plus b. So B equals to 3,000. Now, so the cost as a function of number of toaster produced is equal to 6 times the number of toaster plus 3,000. Okay, so the graph will then approximately looks like the graph will approximately look like this. I want to graph. So the y-intercept is 3,000. The slope is 6. Okay. So this is the number of toaster and this is the cost. That's for part A. Now part B, I continue here. The slope is 6 and that represents the cost of producing each toaster, each additional toaster, I should say. Now the y-intercept, we're supposed to call that cost intercept, is 0,3,000. It represents the fixed cost. We call that the fixed cost. Basically, even if you don't produce any toaster, you still need to pay $3,000. Maybe that's for your building or for your machine to produce the cost, to produce the toaster. Okay, now that's for number 22. Number 23. Oh, I like this question. Number 23, let me circle that first. Okay, find each limit and explain why it does not exist, or explain why it does not exist. So if you are given a graph, you find the limit, then the limit will be, the limit question will be answered by referring to the graph. Okay, basically, do you know how to read the graph and do you know what it means? Okay, so part A, the first part is limit as x approaching 2 from the right hand side. This is x equals to 2. When you approach from the right hand side of that fx, what is the value? 1, 2, 3. It is equals to 3, right? The second part, limit as x approaching -3 from the right hand side again. So x equals to -3. When we approach from the right hand side, the value is going to 0. The y value goes to 0. The third one, the third point, limit as x approaching to -3 of fx, means the two-sided limit. Okay, but the limit from the right is 0, the limit from the left is -2. Then because they are not the same, it does not exist. But the y does not exist because the left hand limit of fx is -2, which is not equal to the right hand limit as x approaching -3 from the right hand side, which is 0. Okay, now point number 4, how about limit as x approaching 4? of the function. This is x equals to 4, right? Notice that the left-hand limit and right-hand limit are both the same, which is equal to 2. So the limit exists because they have the same limit. How about number 5, limit x approaching 0. Notice that if you approach from the right-hand side, it is infinity at 0, the y-intercept, right? When you approach from the right-hand side, it is infinity. From the left-hand side, also infinity. So the limit is infinity. Now, that also tells us that it will become a vertical asymptote later on. Okay, from this graph, you see that we have two vertical asymptotes. The first one is x equals to 0. The second one is this guy. Okay, the second one is that guy. Number 6. Point number 6, limit as x approaching 2 from the left-hand side of fx. This is 2, x equals to 2, but when you approach from the left-hand side, you see that the graph from the left-hand side goes to negative infinity. Okay, now by the definition we saw in, I think, 1.7 or 1.6, that in part B, state the equations of vertical asymptotes. Vertical asymptote is a vertical line, so it has to be stated as the using equation of a vertical line. X equals to 0, x equals to 2. It is incorrect to say that vertical asymptotes equals to 0 and 2. Now that's an incorrect way to express this. I know what you mean, but you still need to write it properly. Okay. Next, at what numbers of the function fx is discontinuous? How that the second one can be vertical asymptotes while there is a point of that? One of the rules to have a vertical asymptotes is that the limit from either side, one of the side, gives you infinity or negative infinity. Okay, so even though we have a function at that point, okay, but if one side give you infinity or negative infinity limit, then it becomes a vertical asymptote. Okay, it gives us a vertical asymptote. Okay, let's review a little bit. I think we have that in 1.6. Do I have that here? Oh, I didn't mention it. 1.7. I don't think I mentioned it yesterday though. So, but yeah, that's actually one of the requirement. Not 1.6. Is it 1.5? I'm trying to find out where I did that. I remember I mentioned it, but I just don't remember if I actually write it down. Not 1 point. Is it 1.6? Maybe I take a look in the book then. Let's take a look at the book. On vertical asymptotes. This is 1.8. This is still 1.8. This is 1.7. 1.6. This is 1.7. This is 1.6. 1.5. This one here. Yeah, this one here. Vertical asymptotes if if one of the limit At least one of them satisfy. Okay, let me enlarge that a little bit. At least one of the following statement is true. So it doesn't mean that the function cannot be defined there. Okay, that is only true for the one that you say that the function cannot be defined there. It's only true for rational functions, but in general, we call that the vertical asymptotes if as we get closer to that x, the value of the function goes to infinity or negative infinity, even if it is only from one side. Okay, even if it is only for from one side. Okay. How that second one can be vertical asymptote when there's a point on that, I just explained it. Can we solve one more question like this after break? I mean, finding the limits from the graph. It's more about your ability to read the graph. So I think instead of just do another problems, how about doing this problem with understanding? Okay, so let's say again, I can do another example, and then you will still ask for another one. So let's go over this again then. Okay, instead. So suppose limit x approaching 2 from the right hand side. X approaching 2 from the right hand side. This is x equals to 2. When you approach the graph from the right hand side, what is the value of the function? Okay, that's for the first part. The second part, as x approaching negative 3. So we take that, we find negative 3. I want to get this line here. When x equals to negative 3. This is x equals to negative 3, right? And then you approach the function from the right-hand side. You approach the function from the right-hand side. What is the value of the function, the y, approaching to when you go from the right-hand side? Approach x equals to negative 3 from the right-hand side. Okay? That's right, that's 0. Now, then, question number 3. Question number 3. Limit x approaching negative 3, but they don't specify from left or right. If it doesn't specify from left or right, then we need to look at both. Okay? Now here we see that the right limit is 0, but the left hand limit is not 0. The right hand limit is, it goes to negative 2. I'm sorry, the left hand limit is negative 2. The right hand limit is 0. Okay? Now, because the left hand and right hand limit are not the same, then they don't exist. Does not exist. Okay? Now, how about when x approaching 4? Now, they don't specify approaching 4 from left or from right, then it must be from both. So when x equals to x equals to positive 4, notice that from the right hand side, it approached positive 2. From the left hand side, it also approached positive 2. So the limit exists and therefore equals to 2. Okay? No, what about that point? The question is not about about that point. The question is about the limit only. The limit means it gets very, very close but not equal to, right? How come the limit as x approaches 4 does not exist considering there's a hole? Okay, now the question of limit does not means you need to know what is the value right at that 4. The limit means it just gets very, very close to 4 but not equals to 4. Okay, does this only relevant to state that it is discontinuous? That's correct. Continuity requires the limit and the value to be the same. Okay, so at x equals to 4, the limit exists. Okay, the limit exists. Let me write it down here. So the limit exists, but because f4 is not equals to 2, which is the limit, then it is discontinuous. Then the function is discontinuous at x equals to 4. But the limit still exists. The limit still 2. Okay, let me see. There's another question. So points are not affecting the limit. The point strike at that point does not affect the limit. No. Because the concept of limit is it's very, very close but not equal to. Okay? I think I emphasized that many, many times already, right? Yeah. The concept of limit is very, very close but not equal to. Okay? Not equal to. So we don't need to worry about what happened right at that point. We need to worry about only when it is very, very close to. That's the concept. Okay? Now, then why on the left-hand side of the other point affected that? Which one? The one here? This one here? When x equals to 2? Is it your question when x equals to 2? Or when x equals to -3? Yeah, when x equals to -3, take a look at the limits. We didn't even mention about what value it is, right? Take a look at the limit. When we approach from the left-hand side, what is the limit? -2, right? When you approach from the right-hand side, what is the limit? Not the same, right? So I don't even, in other words, if you look at this graph here, even if I change this point becomes an open circle, the limit still does not exist. So it's not about what's the value at that point. No, it's about what it approaches to. Okay, what it approaches to. That's the concept of limits. Okay, so that's the difference between what we have here, that's the limit exists, and the one here, the limit exists. Even though the function is defined differently right at 4, but the limit as x approaching 4, the limit is still 2. Okay? Now, what happened when x equals to 0? When x equals, you know what? I think I better use this type and then draw the lines so that we can see better. When x equals to 0, when x equals to 0, as we approach from the right-hand side, the value of the function goes to infinity. From the left-hand side also goes to infinity. That's why then the limit as x approaching 0 from both sides give us infinity. Since there's the plus, there is no function, we are not counting that points. Now, not because there's a positive sign or negative sign. It's just when limit, we never count at that point. We just go close to it, right? But not necessarily equals to. Okay, so the concept of limit never look at the value of the function right at that point. Never, never. The concept of limit is you approach that but not equal to. Okay, so that's for this part A. State part B. Oh, I mentioned it. State the equation of vertical asymptotes. Let me say that again. Vertical asymptotes is a linear equation, so it has to be expressed as the equation of linear equation of a line. Okay, so stating that vertical asymptote equals to 0, 2 is not enough. I know what you mean, but you still need to state it right. In fact, when you write it this way, you are basically saying that you don't see vertical asymptote as a line, you just see vertical asymptote as a number, which is not true. Okay, vertical asymptotes are lines, so it has to be expressed as the equation of a line. Next, at what numbers is fx discontinuous? Take a look. The first one is at x equals to -3, because the left-hand limit x approaching -3 from the left-hand side is not equal to the limit x approaching -3 from the right-hand side. Basically because the limit does not exist. That's one of them. Okay. Second, it also discontinues at x equals to 0. Okay. Why? Because the limit exists. Actually, limit is infinity. Some people call that exist. Some people call that not exist. But for sure, because 0 is not in the domain. Or you can also say that f0 is undefined. Okay, maybe I remind you again, under what situation we say the limit, it is continuous. Fx is continuous at x equals to a if first the limit exists. Therefore, we can say the limit x approaching a of fx exists, and that's equals to fa. Now, implicitly, this statement means the limit exists, the left-hand limit and right-hand limit equal, exist and equal. Second, a is in the domain of the function, so that fa is well defined. The third one is they are equal. So this a function may not be continuous at x equals to a if either one of these fail. Okay, so the first one, x equals to -3, it's failed because the limit does not exist, right? The second, when x equals to 0, it fails to be continuous. It becomes discontinuous there because the second part, x equals to 0, is not in the domain. Now, what happened at x equals to 2? Because the limit does not exist. The left-hand limit and right-hand limit are not equal. And then at x equals to 4 also it's discontinuous because the limit exists and the function is in the domain, but they are not equal. Limit x approaching 4 of fx is not equals to f4. Okay? Now, if we remember the category, the left hand, the first one there, can you explain x equals 2 again? At x equals to 2, notice that the left-hand limit and the right-hand limit are not equal. If you approach from the left, it goes to -infinity. When you approach from the right, it goes to 3, so the limit does not exist. The left-hand limit and right-hand limit are not equal, therefore the limit does not exist. Okay, if we review from our theory again, we usually say that the discontinuity at x equals to -3 is called jump discontinuity. Okay, at x equals to 0, we call that infinite discontinuity because it goes to infinity. Okay, when x equals to 2, you can call that because of infinite discontinuity, or you can also call that jump discontinuity because left hand and right hand limit are not equal. Okay, and the last one at x equals to 4, the limits exist but just not equal. We call that removable discontinuity. Okay, that's for number 23. Number 24, not really my type, but still good to know. Sketch the graph of an example of a function that satisfies all the following conditions. Let me change this into this. So as limit x approaching 0 from right hand side, we get -2. So let's say it looks like this. From the left hand side, we get 1. Right at 0 is -1. At 2, from the left hand side is infinity. Oh, okay, so at when x equals to 2, when we approach from the left hand side, it goes to infinity. Okay, but x approaching 2 from the right hand side is -infinity. Maybe something like this. Okay, so this is x equals to 2. This is -1, -2, and 2. Oh, no, that's not 2, that's 1. Okay, this is an example of a function that satisfies all these conditions here. Okay, that's for number 24. Now the following are my type. In fact, when you study later on, focus on the limits, how to compute a limit. Okay, it will be approximately 40%, even 50% of test 1 about computing the limit. Number 25, limit x approaching 0 of cosine x cubed plus 3x. Limit of a function equals to a function of limit. So this is cosine of limit of x approaching 0 of x cubed plus 3x. And limit of a polynomial, because the domain of a polynomial is all real numbers, therefore it's continuous everywhere, we can just plug that in. Now once you plug in the value x equals to 0, then you don't write the limit anymore. Okay, so this has something to do with this fact that if a is in the domain of the function, then it is continuous there. Okay, therefore the limit as x approaching a of the function is equal to fa itself. Okay, we can say it that way. So if the number you're approaching to is in the domain, then we can just plug that in. The issue is, what if it's not? Okay, what if it's not? Let's say number 26, I'm not sure if that's the case though. Limit x approaching to 3 of x squared minus 9 over x squared plus 2x minus 3. Is it in the domain? I think so, huh? So let's see. So if I plug in 3, that will be 9 plus 6 minus 3, that's not 0. Okay, so it is in the domain, right? So it is in the domain. 3 is in the domain. I just go ahead. I just go ahead. So this is equals to 3 squared minus 9 over 3 squared plus 2 times 3 minus 3. That's 0 over 9 plus 6, 15, 12. That's equals to 0. Okay, but I'm put a note here since 3 is in the domain of that function x squared minus 9 over x squared plus 2x minus 3. But how do we know that x equals to 3 is in the domain, Thomas, of that rational function? Well, because 3 is not a 0 of the denominator. If you plug in 3 on the denominator, you don't get 0. So we can just plug it in right away. Okay, the issue is when it is not in the domain, then what should we do? Like number 27, limit x approaching negative 3 of x squared plus minus 9 over 2x squared plus 2x minus 3. Okay, notice that negative 3 is not in the domain of that function. Okay, because when you plug in negative 3 into the denominator, you get 0. Right? So we'll get undefined. If that's the case, then we cannot we cannot do that. Can you give us time to solve them first? I can, but I need to go up to number 50. So I think one of the way is like you take a look at the recording later on and you pause it. Otherwise, then how long do I need to go for this review? You see what I mean? It goes this way. It goes this way. Okay, it goes this way. Because you may not be that fast. Okay, then I have to slow down, right? But when I slow down, later on somebody may say, Thomas, your test is too long. No, you are too slow. If you're too slow, then speed up. Okay, but what I'm more afraid is like, okay, I need to do this like for very long time, because it's too slow. How about me doing this? How about me doing this? Which part you want me to slow down? Let me know. Or should I give you a break right now? I really need a break though. Let me take a break. Let me take a break. I pause the recording. I'm sorry if I sound a bit upset earlier. Couple reason because it's my Saturday and I feel like this is the time I supposed to go to work. I take a day off because of this, and after this I will go to my work. What happened right now then, my wife is the one substitute me and nobody takes care of my kid, you know. So I try to finish this also so that I can go to work. Yes. My boss yelling at me because of this, like my sushi boss, you know. So well, anyway, let me just go on. Let me just go on. Okay, so in when we compute the limit, if the number the x approaches to is in the domain and the function is continuous around that function that x equals to 0, for example number 25, then we can just plug it in. Okay, likewise for number 26. Okay, 3 is in the domain of the rational functions, and because we say that it is in the domain because when we plug in 3 into the denominator, it doesn't give us 0. So it is well defined. We can plug it in. However, for number 27, it is not in the domain because if we just plug it in, you will see 0 over 0. So how do we do that? Then still work with the limit condition. Try to factor it. In this case, I believe we can solve that by factoring. So you need to know how to factor, okay? And then, yes, because x approaching -3 but not equals to -3, x approaching -3 means x plus 3 approaching 0 but not 0. So we can cancel x plus 3 and we get limit x approaching -3 of x minus 3 over x minus 1. Okay, so this is x. Now I will replace the x by -3 because now x equals to -3 is already in the domain of this simplified version. So -6 over -4, that's 3/2. Okay, that's for number 27. Number 28. Limit x approaching 1 from the right hand side of x squared minus 9 over x squared plus 2x minus 3. As we can see, it happens to be the same expression with number 27, huh? But on the denominator, notice that so the domain of the function is all real numbers except -3 and 1. So yeah, so 1 is not in the domain. So we cannot do this directly. We cannot just plug it in. We need to do it a bit slowly. Okay, keep the limit condition for now. We factor it. Well, x is approaching 1. So x plus 3 is not 0, right? So we have limit x approaching 1 from the right hand side of x minus 3 over x minus 1. Okay, so because x approaching 1 from the right hand side means x is greater than 1. Very close to 1 but greater than 1. Now that means x approaching 1, x minus 1 will be approaching 0 from positive side, right? From positive side. Now, therefore, when I put this in, I will get 1 minus 3, which is -2 over 0 from the positive side. So imagine if we have -2 over positive number 0, -2 divided by 0, but positive. That will give us -infinity. Okay, actually, this is not a correct way to write it. Actually, this is not the correct way to write it. Okay, incorrect way to write it formally. But in my class, write it this way for now, just to explain how we get that -infinity. Okay, oops, I have some writing there. Okay, that's for number 28. Let me go on with number 29. Number 29, limit h approaching 0 of h minus 1 cubed plus 1 over h. Well, if h is 0, you get 0 over 0, so we know we cannot just plug that in, right? So always look at that though. Notice that the way I did number 25, 26, if it is in the domain, just plug it in. If it is not in the domain, then we do it slower. Okay? This is, I think what I will do is I will expand h minus 1 cube. Let me do it aside. Let's do it aside. So h minus 1 cube is equal to h minus 1 times h minus 1 squared. Is it okay? I break that cube becomes squared times h minus 1. H minus 1 squared times h minus 1. Okay. And then notice that I tried to slow down already, right? But I expect somebody to say, yes, it's okay, Thomas. Otherwise, you want me to engage, but nobody engaged me. Then h minus 1 squared is h squared minus 2h plus 1. Okay. The point is like, when I try to expand this, when I try to FOIL this, okay, that may be a long process, so I do it aside first. Okay, I do it on the side. I still need to show that though. Okay, so that will give me h cubed minus 2h squared plus h minus h squared plus 2h minus 1. That is h cubed minus 3h squared plus 3h minus 1. So that's what we have as the yellow part, the one I color yellow there. Now I continue, limit h approaching 0 of h cubed minus 3h squared plus 3h minus 1 plus 1 big over h. Yeah, I basically copy paste whatever I have in the yellows on the yellow color there to the top left. Okay. And then from here, I simplify a little bit on the numerator. Notice that the -1 and +1 cancels, right? Such that we have h cubed minus 3h squared plus 3h over h. And guess what we do next? We have h only on the denominator, right? But on the top, seems like we can factor the h out. Let's do that. Remember, the h equals to 0 is not in the domain in this function, right? So we cannot just plug it in. We cannot just plug it. We need to simplify first. Okay? We simplify first. When we cancel the h, we now have h squared minus 3h plus 3, which is polynomial of h. Okay, and polynomial is a continuous function, continuous everywhere. Then at this time, we can plug in h equals to 0. Okay, that's for number 29. Let me partition this so that when you read it, it's easier to see. Number 30, t squared minus 4, t cubed minus 8. So number 30, limit as t approaching 2 of t squared minus 4 over t cubed minus 8. I think the top one is easy. The numerator is, oh, clearly that 2 is not in the domain, right? Yeah, 2 is not in the domain because on the denominator, if you plug in t equals to 2, you get 8 minus 8, which is 0. In fact, on the numerator as well, you get, if you replace t by 2 right away, you get 0 over 0, which is undefined. to be more precise, cannot be determined yet. Okay, so what I will do is I will do factoring. Now, the thing is, even in pre-calculus level, I saw students cannot factor the denominator. The numerator, of course, should be easy for you, even though I did show students not knowing how to do that. But let me remind you how to factor difference of cubes. A cube minus b cube, when we factor it, is a minus b, a squared plus ab plus b squared. Okay, you learned that in Algebra 1, in Algebra 2, and supposed to be also in college algebra or pre-calculus. Okay, but I know some students don't remember that, that's why I remind you. Okay, now then what happened with t cubed minus 8? Well, t cubed minus 8 is t cubed minus 2 cubed, right? So we follow that pattern. This is t minus 2 t squared plus the t times 2, that's 2t plus 2 squared, which is 4. Okay, so t cubed minus 8 is t minus 2 t squared plus 2t plus 4. Now you see that t is approaching 2 means t minus 2 is not 0. Close to 0 but not 0. Okay, that's what the limit condition for, to remind us, hey, you know what? We are talking about t very close to 2 but not 2. So we can cancel t minus 2 because it's not equals to 0. And we get t plus 2 over t squared plus 2t plus 4. Now, at this point, you see that t equals to 2 is okay if we plug them in, plug that into this function. We don't get 0 over 0. Therefore, let's just do that then. So that's 2 plus 2 over 2 squared plus 2 times 2 plus 4. That is 4 over 4 plus 4 plus 4. That's 4 over 12, which is 1/3. Okay, that's for number 30. Number 31. We have limit r approaching 9 of square root of r over r minus 9 to the 4th. Notice that it is not in the denominator. I mean, it's not in the domain, because when you plug in 9 into this function, you get something over 0, right? So we cannot plug that in right away. Unfortunately, at the same time, there's no way for me, as I can see here, there's no way for me to simplify that any further. So the best way I can do is to plug it in slowly. So notice that r approaching 9, that means r minus 9 is approaching 0, right? Now, the thing is, r minus 9 is approaching 0 from both sides, right? Maybe negative, maybe positive, right? Maybe negative, maybe positive. But imagine, maybe I break it down first. It means r minus 9 is approaching 0 from the left-hand side, and also r minus 9 approaching 0 from the right-hand side as well, because it doesn't specify which direction it is approaching from. Then we need to consider both. Now, the nice thing is this means r minus 9 is negative, right, for this branch here, which if I take it to the power of 4, negative number being squared becomes positive. Is it right? So r minus 9 to the 4th is approaching 0, but it is from the positive side. Likewise, if r approaching 9 from the right hand side, okay, r minus 9 is positive, right, from the right hand side, it means r minus 9 to the fourth is also positive, approaching 0 but positive, so r minus 9 to the fourth approaching 0 from positive side. Now, this means when I plug that in, I will get square root of 9 over 0 positive. Okay, the explanation, why, Thomas, you get this part here? How do you get this? Well, because of this analysis here. Okay, which then will give us 3 over 0 positive, which is positive infinity. Yeah, anything divided by 0 positive, okay, or anything divided by 0 has something to do with infinity, okay? Now, but one extra thing you need to pay attention, is it positive infinity or negative infinity? That's for number 31. Let's see number 32. It's more difficult now, huh? Yeah, because we have the denominator is 0, okay, and we need to pay attention. We need to pay attention with the positive and negative. So limit phi approaching 4 from the right hand side, 4 minus phi over absolute of 4 minus phi. I think we can express this better if we know, if we can get rid of the absolute sign here. Okay, now let's start. Phi is approaching 4 from the right hand side, which means, it means phi is greater than 4, right? Because you approach 4 from the right hand side, and therefore phi minus 4 is positive. If phi minus 4 is positive, then 4 minus phi is the opposite, right? Is negative. Now, if 4 minus phi is negative, then absolute of 4 minus phi is equals to negative of 4 minus phi. Okay. It is based on this definition that we have before, even in pre-calculus, that absolute of x is equals to x if x is non-negative. But if x is negative, to make it positive, we slap that with another negative to make it positive. Okay, so because if x approaching 4 from the right hand side give us 4 minus phi to be negative, then when I try to get rid of that absolute sign, I will replace this guy here by this guy. Okay, this is negative of 4 minus phi. Okay. X approaching 4 means x is not 4. So now I can do the cancellation. When we cancel 4 minus phi, we get negative 1, right? Limit of a constant is just a constant. Okay, so at this point, let me step back a little bit. Let's see how we did this. If the number we are approaching to is in the domain, like number 25 and 26, we can just plug it in. If not in the domain, then we try to simplify and do cancellation until the simplified version contains the number, in this case for number 27. After you simplify that, then you see that negative 3 is in the domain. Then you can plug it in. Okay. Number 28, however, even after we simplify that, It's still not in the domain. So then we try to take a look, okay, well, even though it is not in the domain, take a look what happened when x minus 1, what happened to x minus 1. Is it approaching 0 from positive side or from the negative side? Okay, then we see that it will go to, in this case, negative infinity. Okay, number 29, we basically, well, 0 is not in the domain of this function, so I simplify first until we are lucky in this case, like when I simplify, I get a polynomial which is continuous everywhere. So after we get the just polynomial, we plug it in. That's for number 29. Number 30, the same thing. 2 is not in the domain of the function. So I try to simplify, in this case, by factoring. One thing you need to remember how to do factorization of sum or cube of sum or difference of cubes. Now, in this case, after we do the cancellation, we got a rational function whose domain includes t equals to 2. So I just plug that in. Okay, number 31, even though it takes only 2 or 3 steps as you see here, is actually the hard one. Why? Because 9 is not in the domain of the function, and at the same time, there's no way for us to simplify that. So I have to do this analysis, like when r approaching 9, then r minus 9 approaching 0. Because there is no notation approach from left or right, I need to consider both cases. Okay, in both cases, what will happen to r minus 9 to the 4th? Okay, and then you see, because both of them goes to 0 positive, then when we plug that in, we get positive infinity. Now, what happened, by the way, what happened if, just for curiosity, what happened if this were cube? If that were cube, then r minus 9 cube will be 0 from the left hand side, okay, for the first case, and r minus 9 cube will be 0 from the right hand side for the second case. Now in that situation, the left hand limit and right hand limit does not exist, and the limit of this function does not exist. Okay, because one of them goes to 0 negative and the other one goes to 0 positive. Okay, this will be negative infinity. This is positive infinity. Because the left hand limit and right hand limit are not equal, then the limit does not exist. That's if I change this exponent, instead of 4 becomes 3. Okay, now in number 53, we have absolute value. And for absolute value, we need to be a bit careful. We need to get rid of that. Okay, we need to get rid of that absolute value and see what we replace that by. Okay, so I did this analysis. Well, phi is greater than 4, so phi minus 4 is positive. Therefore, 4 minus phi must be the opposite of that. Now, that tells us if I replace absolute of 4 minus phi, I replace it by what? Okay, when I replace that, notice that 4 minus phi cancels to be negative 1. And then we get the quotient becomes negative 1. And therefore, I can just plug that in. Okay, that's the principle though. So far, that's the principle. I hope that's enough for us to move on with number 33. Number 33, we have limit r goes to negative 1 for r squared minus 3r minus 4 over 4r squared plus r minus 3. Let's try to factor this. So one of the prerequisites for this class is pre-calculus or college algebra, at which one of the component you should be very, very fluent in factoring already. Okay, I can understand for not supposed to, but based on what I have seen so far, some students forget how to factor difference of cubes or sum of cubes. That's why I reminded you here, right? But for quadratic, I assume you are quite fluent. Okay. Okay. R approaching -1 means R approaching -1 means R plus 1 approaching 0, but not 0. Okay, so we can cancel that. And now we have limit of R approaching -1 of R minus 4 over 4R minus 3. Now, notice that -1 is now in the domain of this function, so we can just plug that in. That's -5 over -7, simplifies to be positive 5 over 7. Is it okay? I'm recording this, right? But please do. Yes. Number 34. Limit t approaching 5 of 3 minus square root of t plus 4 over t minus 5. Yes, t is not in the domain, so we cannot do it directly. And we have radicals here. So if you remember in class, what do we do if we have radicals? Like if one the numerator or denominator have conjugate, then we try to multiply by the conjugate first. And you need to show that we multiply that to the top and the bottom. Okay? Because we basically multiplying by 1 such that we don't change the value. But we change the structure. Okay? We don't change the value, but we change the structure. Okay, limit t approaching 5. On the numerator, we have 3 difference of squares, right? So 3 squared, which is 9. Maybe I write it this way first. 3 squared minus the square of the square root. On the denominator, I will just write it as product. And then let's simplify. This is limit t goes to 5 of 9 minus t minus 4 over t minus 5 of 3 plus square root of t plus 4. Let me continue here. This is limit t goes to 5 of 5 minus t, 5 minus t over t minus 5 square root of t plus 4. Notice that t minus 5 and 5 minus t are opposites and not zeros, right? Because t approach 5s means t minus 5 approaches 0 but not equals to 0. Okay, so when we do the cancellation there, we get extra -1. Is -1 over square root of t plus 4. Maybe I explain a little bit. A minus b is the opposite of b minus a. Okay, so if we subtract in reverse direction, like t minus 5 and 5 minus t, they are actually opposite. When we cancel them, we get extra -1. Now, notice that in the new function, 5 is already in the domain, right? So we can just plug that in. That's -1/3. Okay, so if it's already in the domain, we can plug that in. If not, we need to simplify first. It's a long journey, so be patient with me. Okay, I try to do it fast, but at the same time, thank you for asking me to slow down. I cannot get too slow though. That's the thing. Okay, number 35, limit s minus 16 of 4 minus square root of s over s minus 16. So you notice if I replace s by 16, I get 0 over 0. So that's not the right way to do it, right? Okay. What I can do, however, I multiply by the conjugate on the top and the bottom. So 4 plus square root of s, 4 plus square root of s on the top and the bottom. Okay, and then limit s goes to 16 on the numerator. When I multiply that, that's 16 minus s, right? Difference of squares. At the bottom, I have s minus 16 times 4 plus square root of s. Now, notice that s is approaching 16 but not 16 means s minus 16 are not 0 and 16 minus x are not 0. So we can cancel that under limit condition and we get -1 over 4 plus square root of s. Now I can plug that in already. -1 over 4 plus square root of 16. That's -1 over 4 plus 4, which is -1/8. You know what? Let me move this. Okay, that's for number 35. I think number 35 and 34 are basically the same idea, even though number 35, I think number 35 is easier. Number 36, limit of phi approaching 2 of phi squared plus 2 phi minus 8 over phi to the 4th minus 16. Now 2 is not in the domain, so I try to factor. The numerator, I get phi plus 4 phi minus 2. On the denominator, that's difference of squares. Oh, you know what? I think it's more complicated than just difference of squares. Let me see. So that's, I do it aside though. Okay, so that's phi squared plus 4 phi squared minus 4. When I factor further, that phi squared plus 4 phi plus 2 phi minus 2. Okay, that's the one. The phi squared plus 4 phi plus 2 phi minus 2. Okay, now phi minus 2, phi is approaching 2, which means phi minus 2 is approaching 0 but not 0 yet. So I can cancel that phi minus 2. Okay, and under the condition of limit, we get phi plus 4 only on the numerator. At the bottom, we get phi squared plus 4 phi plus 2. Now we can plug in numbers already, right? Okay, we can plug in numbers already. So we get 2 plus 4 and then 2 squared plus 4 times 2 plus 2. That is 6 over 4 plus 4 is 8, 2 plus 2 is 4. You know what? Let me cancel by 2. So that's 3 over 16. Okay, that's for number 36. I think number 37 is very similar. Very similar. So number 37, we have limit x approaching 0 of 1 minus square root of 1 minus x squared over x. If I plug in x equals to 0, I get 0 over 0. So no, that's not what we will do. However, I see that on the numerator it has a conjugate, so let me multiply by the conjugate first and see what happened. That's limit x approaching 0 of 1 minus x squared. The square root cancels, right? When you square it. And at the bottom we have x times 1 plus square root of 1 minus x squared. Limit x approaching 0. The 1 cancels. I get x squared over x times 1 plus square root of 1 minus x squared. We can cancel one of the x on the top and the bottom, right? Because x approaching 0 means it is not 0. It is just approaching it. So we get limit x approaching 0 of x over 1 plus square root of 1 minus x squared. Now you can see when I plug in 0, we don't get 0 over 0, right? Then we just plug it in. Basically, x equals 0 is now already in the domain of this function. I can plug that in. Yeah, 0 over 2, which is 0. That's for number 37. Number 38. Let me give myself some space here. Number 38. Limit x approaching 1 of 1 over x minus 1 plus 1 over x squared minus 3x plus 2. We need to put them together first. One thing you should not do is like, oh, limit of sum equals to sum of limit. So the following is a wrong way to do it. If you say limit x approaching 1 of 1 over x minus 1 plus limit x approaching 1 of 1 over x squared minus 3x plus 2. This is wrong. This is wrong. Why? Because if you think about this, you will see the limit of this function does not exist, and the limit of this function also not exist. Okay? We can only split the sum of the limit of sum to be sum of limits if the limit exists. Okay? If the limit exists. If the limit does not exist, we cannot do that. Okay? The existence of limit is the one allowing us to split that. Okay? Now, this is equals to limit x approaching 1 of, what I will do is I will combine these two fractions here. So to do that, I need to find the LCD first, right? And to find the LCD, I need to do the factoring first. Okay, now to put them together, it means the first fraction needs to have LCD x minus 2 as well. So that would be x minus 2 over x minus 2 x minus 1 plus 1 over x minus 2 x minus 1. Okay, let me slow down a little bit. What I did, simply multiply the top and the bottom by x minus 2 for the first fraction. The reason is because the LCD of this expression is x minus 2, x minus 1, right? Okay, so I get the LCD, so I need to adjust the numerator. Now we already have common denominator. We can put them together. We can actually add them. So on the denominator, x minus 2, x minus 1. On the numerator, we have x minus 2 plus 1, which simplifies to be limit x approaching 1 of x minus 1 over x minus 2 times x minus 1. Now, I hope you can tell what to do from here. Okay. X is approaching 1 means x minus 1 is approaching 0. That implies x minus 1 approaching 0. But while it is approaching, then it's not equal to, right? I repeat that too often such that you're supposed to know that already. So we can cancel that x minus 1 on the top and the bottom. Now you see that 1 already in the domain of that simplified function. I can plug that in now. Okay. Now I go on number 39. Suppose we have a function that is bounded above by 2x by x squared and below by 2x minus 1 for x between 0 to 3. Now what happens if your limit approaching 1? Notice that 1 is in this interval, right? Okay, so when I apply limit x approaching 1 of that 2x minus 1, it must be less than equals to limit x approaching 1 of fx, which is less than equals to limit x approaching 1 of x cubed. I'm sorry, x squared. Right? Because 1 is in the interval, and they said in that interval this inequality applies. Right? Okay, so if I apply the limits, the inequality should be maintained. But the limit on the left-hand side here, you just plug in numbers because it's in the domain. That's 2 times 1 minus 1, that's 1. And on the right-hand side here, the limit of x squared as x approaching 1 is just 1 also. Okay, so by squeeze theorem, limit as x approaching 1 of fx must be equals to 1 because it is less than 1, less than equals to 1, and greater than 1, greater equals to 1 at the same time. We are basically this function, this limit is being squeezed by the same number above and below. Then the limit must be just that number. Okay, the nice thing with number 39, they tell us the upper bound and lower bound that squeeze the function. Number 40, however, is not. Okay, number 40 is not. They don't tell us the upper or lower bound, but when we take a look at this, cosine of 1 over x squared, prove that this limit is 0. Well, cosine of 1 over x squared is at least -1, at most 1 for x not equals to 0, right? As long as x is not equals to 0, cosine of this function should range between -1 to 1. Now, if I multiply each part of that inequality by x squared, I will get -x squared is less than equals to x squared cosine 1 over x squared less than x squared. And if I apply the limit as x approaching 0 of -x squared, of limit of x approaching 0 to all three parts of that inequality, notice that the upper bound and lower bound goes to 0. So even we know that x equals to 0 is not defined at, even if we know that x equals to 0 is not in the domain of this function, we still can compute the limit. Okay, in this case, by squeezing it from above and below. If you use squeeze theorem, you need to express explicitly when you come to the conclusion. So by squeeze theorem, limit x approaching 0 of x squared cosine of 1 over x squared is 0. That's for number 40. Oh, by the way, did I circle this 25 to 38? Actually, everything here also, I like this. Okay, as I remember, everything after this is the type of question you should expect in your tests. Okay. Now, number 41 to 44. Prove the statement using precise definition of limit. I think I want to say it this way. This type of questions should be tested. Okay, but I plan to put this in your test, to put these type of questions in your turn-in homework, because it takes too much time and I need you to think more. Okay, now so 41 to 44, that's actually the type of question that I like to ask, but I will only ask that if I do, it will be only in turn-in homework. Okay, because I want you to think about it. Okay, we went over this yesterday and I want to go over this again. Number 41 is the linear function, so it tends to be on the easier side. For number 42 is the cube root function. You will see that's actually not that easy, but not that bad either. Okay. Number 43 is the quadratic function. That's the one painful yesterday when we did section 1.7. Number 44, this is the limit goes to infinity. I did not cover this yet yesterday when I went over section 1.7. When I went over section 1.7. Is it 1.7 or 1.8? 1.7, that's right. Where limit goes to infinity. Okay, but I will do that here. So, number 41. Number 41. Okay. Again, this may be in your turn-in homework. I promise you, I will not ask this in your test. Okay. Proof that limit x approaching 2 of 14 minus 5x equals to 4 using the definition of limit. Okay. Now, so remember yesterday when we tried to prove the limit is, in this case is 4 using definition of limit, we do it in 2 steps. The first step is we need to plan to find delta in terms of epsilon. Okay, and in the second step, we need to show the delta we chose works. Okay, so let epsilon be any positive number. Okay, need to find delta in terms of epsilon. That's what we will do. Okay, such that as long as absolute of x minus 2 less than delta, we get absolute of 14 minus 5x minus 4 to be less than epsilon. Okay, let's simplify this. This is absolute of 14 minus 4. 14 minus 5x minus 4, that is equal to absolute of 10 minus 5x, that is equals to 5 absolute of, 5 absolute 2 minus x. I see the something in the chat. I don't know yet though. I don't know yet. Okay, but delta to be negative epsilon, I don't think that's what we will do. You know, because you will see later on delta has to be a positive number too. Okay, so we cannot choose a delta to be a negative number. Okay, we cannot use delta to be a negative number. Now, on the other hand, well, you see that absolute of x minus 2 is just the same to absolute of 2 minus x. Okay, so this is, we can say that this is absolute of, therefore, absolute of x minus 2 is less than e over 5, right? We choose delta equals to epsilon over 5. Okay, now let me do the second step on the right hand side. Oh, you know what? I'm gonna use the right hand side for number 42. So I go on with the further down. So step 2 need to show that the delta we chose actually works. Okay, so let epsilon be any arbitrary positive number. We choose delta to be epsilon over 5. Okay, such that if absolute of x minus 2 is less than epsilon but still positive, which means x minus 2 is not 0, then absolute of 14 minus 5x minus 4 equals to 10 minus 5x equals to 5 times absolute of 2 minus x. That is less than 5 times delta. Okay, according to the if here, right? the if here. But at the same time, according to our choice of delta, 5 times delta is 5 times epsilon over 5, which is epsilon. So we already get if absolute of x minus 2 less than delta but not 0, then absolute of 14 minus 5x minus 4 is less than epsilon. This gives a complete proof of why we can say the limit as x approaching 2 of 14 minus 5x is equal to 4. Okay, so we need to first find the delta in terms of epsilon, and second, we need to show that delta satisfies the definition of the limit. That's for number 41. Number 42. Limit as x approaches 0 of cube root of x equals to 0. Let's plan that. Let epsilon be positive. We need to find delta in terms of epsilon such that if absolute of x minus 0 is less than delta but not 0, then absolute of cube root of x minus 0 is less than epsilon. Okay, but let's actually say this. Absolute of x minus 0 is just absolute of x, right? And absolute of radical 3 minus 0 is just absolute of radical 3. Is it right? Okay, and this is equals to the cube root of absolute of x. Is it right? Think about this. The cube root of radical for cube root. The cube root of absolute is absolute of cube root. It works for every odd roots. Okay, so from here, then we can use absolute of x is less than epsilon cube, right? If you cube both sides. So choose delta equals to epsilon cube. Now then, we need to show that this choice of delta in terms of epsilon works. Let epsilon be any positive number. We choose delta to be epsilon cube such that if absolute of x minus 0 is less than delta and still positive, then absolute of cube root of x minus 0, that is absolute of cube root of x, that is cube root of absolute of x, this will be less than cube root of delta. But delta itself is e cube, epsilon cube, which is equals to epsilon. Okay, so if absolute of x minus 0 less than delta and not 0, then we get absolute of cube root of x approaching minus 0 is less than epsilon. Therefore, it completes the proof. Okay, I think number 41 and 42 are actually on the easier side. Number 43, as you will see very soon, is actually on the complicated side. Okay, but I went over this in section 1.7 though. Okay, so let's go over this, the plan part. Let epsilon be positive. Need to find delta in terms of epsilon. Such that if x minus absolute of x minus 2 is less than delta, you may wonder why x minus 2 times, because of this. And not 0, then absolute of x squared minus 3x plus 2 is less than epsilon. Okay, let's work this out. I definitely need larger space. So this is equals to absolute of x squared minus 3x plus 2. That is absolute of x minus 2, x minus 1, which is absolute of x minus 2 times absolute of x minus 1. Now I already have absolute of minus x minus 2, which will give us the less than delta, right? This is our delta. This is our less than delta. But what happened with this? Right, that's the issue for now. Then let's do the analysis. So we know that x minus 2, absolute of x minus 2 is less than delta. Okay, we set delta to be at most 1, such that now absolute of x minus 2 will be less than 1. Therefore, x minus 2 is between -1 and 1. I'm sorry. Yeah, and then x will be between 1. If I add 2, then x between 1 and 3. But what we need is what to replace this by, right? Okay, so we use absolute of x minus 2 to find out what will x minus 1 be. Okay, we need to replace this by a number. Need to find an upper bound. Okay, and it doesn't have to be 1 here. You can choose, say that delta is at most 2 or at most 1/2. Of course, you will get different upper bound, but as long as it is an upper bound. Okay, so if I subtract by 1 here, it will be at most 2, at least 0. So we can say absolute of x minus 1 is at most 2. Okay, now coming back here, then this is less than absolute of x minus 2 times 2. Okay, this is the upper bound of absolute of x minus 1, right? Now, we want this to be less than epsilon. So absolute of x minus 2 should be less than epsilon over 2. So we choose our delta to be epsilon over 2 or 1, whichever is smaller. Whichever is smaller. This is actually the way we say that delta is less than epsilon or less than equals to epsilon over 2, or delta is at most 1. Okay, then it satisfies both of those conditions. Okay, now in step 2, the proof part. Let epsilon be a positive number. Choose, or let delta be the smaller of the epsilon over 2 that you give me, or 1. Notice that this expression again means that delta is at most epsilon over 2, and at the same time delta is at most 1. Okay, such that if absolute of x minus 2 is less than delta but not 0, then absolute of x squared minus 3x plus 2 is absolute of x squared minus 3x plus 2. I will factor these and write them as product of absolutes. Okay, but we already know that absolute of x minus 2 is less than delta, and delta is at most 1, means absolute of x minus 2 is at most 1. So x minus 2 is between negative 1 to 1, actually less than 1. So x is between 1 and 3, and x, sorry, it should be minus 1, not plus 1. This is x minus 1 when I factor it. So x minus 1 is between 0 and 2. So absolute of x minus 1 is at most 2. This is at most 2 times absolute x minus 2. But we also know that absolute of x minus 2 is less than delta. Okay, and we know delta must be less than equals to epsilon over 2. So at this point we already shown that if absolute of x minus 2 less than delta but not 0, then absolute of x squared minus 3x plus 2 is less than epsilon. Therefore, completes the proof where we, for every epsilon, we can find a delta in terms of epsilon, and that delta that we chose actually works. Okay, now number 44 is the one I didn't explicitly mention that when we work with the limit in 1.7, but the definition when the limit is infinity is as follows. Okay, limit x approaching a of fx equals to infinity means it is infinity, right? For every number, positive number that you choose, however large it is, okay, there is an x such that as long as that x is close enough to a, less than delta, but still positive, then fx minus fa, no, it's actually fx is greater than m. Here's the logic. Suppose we have an asymptote case, right? And you see the limit of this function is actually infinity if you approach that from the left-hand side. Okay, the idea is this. When we say the limit is infinity, it's like you choose whatever m you like, as large as you want. Okay, then I can always find another number closer to a that give me the higher value than m that you chose. For every number you chose, the positive number m you chose, I can find another x such that fx is greater than that number. Okay, let's take a look at our textbook where it says that. I believe that's in 1.7. Let me fast forward a little bit. I'm looking at the book right now. I try to quote you the statement of that because I think I didn't mention that when I went over 1.7. Give me a second. It's on page 80. Let me quote that and post it there. Yeah, this is the statement of the function. This is the statement. Let f be a function defined on some open intervals containing a, except possibly at a itself. Then the limit of the function is infinity, means that for every positive number m, there is a delta such that as long as x is distance from a is less than delta, the value of the function is even larger than the number you chose. You chose the number, I can give you an x that give a value even larger than that number. Okay, so this consists of two steps also. First, the planning part, plan. Let m be an arbitrary positive number, and you, because it's positive infinity, you want the m, you chose a very large number that you like. Okay, we need to find the delta in terms of that m such that as long as that x minus 4 is less than delta, as long as the x is close enough to from 4, then fx is greater than m. Okay, so fx here will be 2 over square root of x minus 4 greater than m. Okay, multiply both sides by square root of x minus 4. But notice that x is approaching 4 from the right hand side. Therefore, x is greater than 4. Is it right? X minus 4 will be positive. Therefore, x minus 4 will be approaching 0 from the positive side. It means it's positive number. Okay, now, so if I multiply both sides of this inequality by square root of x minus 4, which is a positive number, we maintain the inequality sign. We don't need to reverse inequality sign. Divide by m, which is a positive number. Now I square that. Okay, So x minus 4 is less than 2 over m squared. Okay, so the choice we have is I need the delta. So choose delta equals to 2 over m squared. Think about this. So this is absolute of x minus 4 is less than 2 over m squared, right? We want this to be less than delta, okay? This is the less than delta, so we choose that way. Okay, now let's see if this choice actually works. So proof, let you choose the number you want, the large capital M you want. We then choose the delta to be 2 over m squared, such that as long as absolute of x minus 4 is less than delta, then our fx, which is 2 over square root of 4 minus x minus 4, this will be equals to what? See, if I want to say this, if square root of absolute of x minus 4 is less than delta, square root function is increasing function, so this is less than square root of delta. The reciprocal, however, we need to reverse the inequality. You see what I mean? Okay, so this will be greater than 2 over square root of delta. Okay, but square root of delta is 2 over m, which is then we get m. Okay, so if absolute of x minus 4 is less than delta but not 0, we choose this way. Okay, then the outcome is then fx is greater than whatever m that you chose. You chose a number, I can find a delta such that any x whose distance from 4 is less than delta, that x must give us a value larger than what you chose. Okay, now that's for a limit involving infinity. Number 45. This time we don't have the graph. Oops, hold on. I want to point something. This time we don't have the graph, but we have the function. So it's basically about we need to know which function to use. Okay, so now part A. What is limit x approaching 0 from the right hand side? Okay, so this notation means x is close to 0 and x is greater than 0 because it's from the right hand side. Okay, which means we use this function. Okay, so limit x approaching 0 from the right hand side of fx, that is equals to limit x approaching 0 from the right hand side of the function 3 minus x. So a piecewise defined function, that's what we start with, and we see which value we use from which side to know which function to use. And then from there we say, oh, you know what, this is already a polynomial, so I can just plug in the numbers. That's 3 minus 0, that's equals to 3. Okay, for part B, limit x approaching 0 from the left hand side of fx, from left hand side of fx. Okay, this means x is close to 0, but x is less than that 0. You approach from the left hand side, right? Okay, so we will use this one here. This is limit x approaching 0 from the left hand side of square root of negative x. It is in the domain, so I can just plug that in. That's square root of 0, that's 0. Part C, how about the two-sided limit? Limit x approaching to 0 of fx. Now we say, because the left-hand limit is 0, the right-hand limit is 3, we say the limit does not exist. Okay, let me explain. Because the left-hand limit, x approaching 0 from the left-hand side of fx, is not equals to the limit as we approach from the right-hand side. Okay, now later on you will see that the function is discontinuous. When we need to answer part B, we will say that it's discontinuous. F is discontinuous at x equals to 0 at least. Maybe another one. Okay, let's see part D. I'm sorry, I write the wrong notation. This is A, I supposed to say A1, 2, 3. Now I work on part 4 of part from A. Limit x approaching 3 from the left hand side of fx. This means x is close to 3. X is close to 3. And you approach that from the left hand side means the x is less than 3. Okay, x is less than 3, we will use this one. So this is limit as x approaching 3 from the left hand side of 3 minus x. I can just plug in the number, that is 0. Okay, and part 5, how about limit as x approaching 3 from the right hand side? Means x is greater than 3. X is greater than 3, I will use the last piece of the piecewise defined function. Limit x approaching 3 from the right hand side of x minus 3 squared. It's continuous, so I just plug that in. X 3 minus 3 squared, that's equals to 0. Now what happened to the limit as x approaching both sides of 3? Well, you see the left hand limit and right hand limit are the same, so we say the limit exists and equals to 0. Okay, let me explain further. Because limit x approaching 3 from the left hand side of fx is equal to 0, which is also the limit when we approach 3 from the right hand side. Okay, now this function is continuous everywhere, right? In the interval, so we say where is this function discontinuous? It is only discontinuous at x equals to 0. Can we try to sketch the graph? Let's see. On the left hand side, we get square root of negative x, not including 0. Okay, that's square root of negative x. 3 minus x, y-intercept is 3, the slope is 1. So it goes down like this. And then the third piece is x minus 3 squared when x is greater than 3. X minus 3 squared is x squared moved 3 units to the right. So it will be like this. Okay, so this is x minus 3 squared part. This is 3 minus x part, and this is square root of negative x part. Okay, oh, and it's continuous there. Okay, so the only place that it is discontinuous is at x equals to 0. That's for number 45. Let me go on. Number 46. You try this yourself, but this is actually my interest. Okay, similar to this is similar to number 45. Okay, I give you the sketch of the work. They actually give us the hint. For each number 2, 3, 4, determine if it is continuous from the left, continuous from the right, and continuous at that number. So what you need to do for part A, you need to check at each of the endpoints here. So notice that the domain is from 0 to 2, and then continue again from, oh, not including 2. Oh no, including 2, I'm sorry. The first part including 2. Union from 2 to 3, including 3, union not including 3 up to not including 4, union from 4 to infinity. Okay, so we need to check what they say is that we need to check at 2. Okay, so limit x approaching 2 from the left hand side of the function. How about limit x approaching 2 from the right hand side of the function? Therefore, does the limit exist at 2? Okay, and then at 3, limit x approaching 3 from the left hand side. What is the value? Limit as x approaching 3 from the right hand side. What is the value? And then if they're the same, the limit exists. If not the same, the limit does not exist at 3. And you do likewise to 4. Limit x approaching 4 from the left hand side. What is that equal to? Limit x approaching 4 from the right hand side. What's the value? And if the limit approaching 4 exists. Okay, and then from there you sketch the graph. That's for number 46. That's one of the question I have interest in, but I will not work it out anymore, because it's very similar to number 45. Okay, number 48, 47 and 48 show that the function is continuous in its domain and state the domain. Number 47 first. What's the domain? The hx is the fourth root of x plus x cubed cosine x. The domain is including 0, but not negative, because fourth root, right? That's including 0 to infinity. Okay, that's the domain. What we need to now show is that it is continuous in the interior. Okay, let's write down the plan. We need to show that it is continuous in the interior of that interval from 0 to infinity, and it is continuous from right for the left endpoints, the lower bound, when x equals to 0. Okay, so that's the first step, that's the second step. And to show that it's continuous, we just need to show that the limit exists and equals to the function. Okay, so plan number 1. So let x be an element in the interior. You choose any point in there. Okay, not x, use a. Now, limit as x approaching a of the hx equals to limit x approaching a of fourth root of x plus x cubed cosine x. This is equal to limit of sum is sum of limit. You may say, oh, Thomas, can we just say that A is already in the domain, so it must be continuous? We cannot, because that's what they ask us to show. The question is not about what is the limit. The question is like, why is it continuous? Okay, so the continuity is the one in question. We need to show that. So we use the limits property. The limit of sum equals to sum of limits. Okay, and then this is the fourth root of limit of x approaching a of x plus limit of product equals to product of limits. Okay, this gives us the fourth root of a plus a cube times cosine a. But this is just the same to HA though. So from here we say, so the function is continuous on, because we choose any a in that interior, and this works means any element in this interior is continuous. The function is continuous on that interior. The second part, what happened at the endpoint? Okay, what happened at the endpoint? Limit x approaching 0 from the right hand side. You see, because the interval is from 0 to infinity, right? Okay, so we cannot check the limits from both sides of 0 because it is undefined on the left hand side. We can only do the continuity from the right. We are checking the continuity from the right only. Okay, so look at the limit of hx as x approaching 0 from the right hand side. Okay, this is limit x approaching 0 from the right hand side of square root of x plus x cubed cosine x. The gadabam gadaboom, basically we did the same thing. We will get this is h0. Okay, so hx is continuous from the right at x equals to 0. Now using this point 1 and point 2, then we can say this function, so hx is continuous on 0 to infinity. Okay. Number 48, I don't think I will do that in full. I give you the sketch of the work. Notice that the domain of this function is all real numbers except when x squared minus 2 equals to 0, which means x squared cannot be 2 and x cannot be plus minus square root of 2. Okay, so the domain is negative infinity up to negative square root of, negative square root of 2 union square root of 2 to infinity. Now, because this is not an open interval, it means you will just do the interior. Okay, it's an open interval, right? Not closed. There's no endpoints for this. We have endpoints, but the endpoints is not included in the domain. So we just need to do the first step. We just need to do the first step. Okay, so we just need to show that it is continuous in the interior, but these intervals here are open set, right? Negative infinity to negative radical 2 union radical 2 to 0 infinity. We don't need the endpoints. Don't need to check the endpoints of the interval because the endpoints not in the domain. The endpoints not in the domain. So that's the nice thing about having an open interval as a domain. If we need to check the continuity, we just check the interior, and right at the endpoints, because it's not part of the domain, we don't need to check the continuity there. Okay, that's for number 48. Number 49 and 50. Use intermediate value theorem to show that there is a solution of the equation in the given interval. Intermediate value theorem says the following. Just to remind ourselves, intermediate value theorem says this. If fx is continuous, on an interval AB, a closed interval AB, where FA is not equals to FB, try to visualize that. So let's say this is A, this is B, the value of the function are different. Okay, then whatever number you choose in between, I can always find there must be a C in that interval AB that gives you there is for every, I think I should say for any n in that interval in the range, there is a C such that Fc equals to n. Okay, so I think I would just do one of this 49, number 49. I do both of them. So number 49. Okay, we have this x to the fifth minus x cubed plus 3x minus 5 equals to 0 in the open interval 1, 2. Okay, let's define this first. Let fx equals to the function x to the fifth minus x cubed plus 3x minus 5. Okay, now f1 equals to, if I plug in x equals to 1, that's 1 minus 1 plus 3 minus 5, that is negative 2. f2 equals to 2 to the fifth minus 2 cubed plus 3 times 2 minus 5. That's 32 minus 8 plus 6 minus 5. That is what? 25. Okay, think about this. So we have f1 is negative 2, f2 is 25, and the function is continuous, right? So there must be a value between 1 and 2 such that f of that value equals to 0. Okay, since 0 is between negative 2 and 25, why 0, Thomas? Because of this 0. Okay, then by intermediate value theorem, there is C in the interval of 1 and 2 such that fc equals to 0. Okay, so intermediate value theorem does not tell us what is that value, but it just guaranteed there must be some guy. Okay, all I need to show is that the value at the endpoints makes that 0 is in between. Okay, or another way to say that the value at the endpoints are the opposite sides of the number we want. Now let's take a look at number 50. You will see the idea is very similar. I will not give myself a break anymore because I will just finish at number 51. Number 50, we have 2 sine x equals to 3 minus 2x, and there's a solution in that interval 0, 1. Okay, we do it this way first. To solve that equation, maybe solution 2 sine x equals to 3 minus 2x is the same equation to 2 sine x minus 3 plus 2x equals to 0. Oh, you know what? No, I don't want to make it 0. It doesn't have to be. You can, but it doesn't have to be. Make it like this. Make it like this. Plus 2x equals to 3. Now we define a function. Let fx equals to let fx equals to 2 sine x plus 2x. Now what is f0? Is 2 sine 0 plus 2 times 0, that's 0. Okay, but at 1, that's 2 sine 1 plus 2 times 1. I don't know what's that though. Let me use my calculator. Now the one there is in radian. So when I use my calculator to find the estimation, give me a second. This has to be in radian. Okay, it's already in radian. So 2 sine 1 close parenthesis plus 2 times 1, that's 2, that's equals to 3.68 something. 3.68 something. Okay, now since the number 3 to which the equation should equals to, since that 3 is between 0 and 3.68 something, then by intermediate value theorem, there is a number in the interval between 0 to 1 such that FC equals to 3. Okay, basically because 3 is in between F0 and F1, then there must be a C that gives us that value 3. Okay, that's for number 50. I will finish it in number 51. Suppose that fx, absolute of x, fx is less than or equals to g for all x. Find the limit of fx. Absolute of fx is less than or equals to gx, right? So if I apply limit of x approaching a of absolute of fx, that is less than or equals to the limit of x approaching a of gx. Now, limit of x approaching a of absolute of fx is therefore less than or equals to 0. Right? Okay, maybe I also write it this way. Absolute value is always greater or equals to 0, right? That implies by squeeze theorem, limit of x approaching a of the absolute value is equals to 0. Okay, but we are not done yet because the question is what is the limit without that absolute value? Okay, then we need to have another thing. Limit of absolute value is absolute value of limit. Okay, remember absolute value is a continuous function, right? But if absolute value of blah equals to 0, then the blah must be 0, right? So from there, limit x approaching a of fx is equals to 0. Therefore, we have proven it. Okay, this is also the proving type. This is a more abstract squeeze theorem. Okay, it is a more abstract squeeze theorem, which we actually, when we did that somewhere earlier. Where's that? I remember we did this. Here, number 37, 38 and number 40, we did squeeze theorem. Okay, but in number 39, they give us the upper bound and lower bound. In number 40, they don't tell us the upper bound and lower bound, but they give us the function. Okay, in the last question, however, you're welcome, Sean. In the last question, however, it's a very abstract function. Okay, it's very abstract function. Now, just remember that absolute value is always non-negative. So it's already have a lower bound. Okay, the information they give us here is another is the upper bound. Okay, and therefore we can squeeze that down to 0. Okay, this is where I will stop, and I hope it helps you later on for your test 1.